Greetings everyone. In this video, I will be discussing about scalable consensus mechanism. I will start by explaining what consensus mechanisms are, then I will go over how we can reach consensus in the presence of failures. Finally, I will conclude by discussing scalable solution to the consensus problem. Now let's look at consensus and why is it essential. Consensus is useful for several reasons. For example, it can determine the leader of multiple machines. It can also be used to coordinate an attack. Many problems similar to consensus exist in distributed computing literature. Some examples include executing global application, ordering messages received at different locations so that the information they convey makes sense, or synchronizing multiple machines to take collaborative actions. In order to understand it in a better way, let's assume three nodes P1, P2, P3. Here, the view they have on the same blockchain may differ. In this example, we can see nodes P1 and P3 disagree on the block that gets appended after B2 in the chain. All these can be summarized with the help of a directed acyclic graph, or DAG. This DAG results from the union of vertices and edges of all these blockchain views. As you can see, that this DAG consists of forks. The problem associated with forks is that they can lead to double spending. Let us consider a scenario in which Bob and Carol are two merchants who sell real goods in exchange of coins. Let Alice be a malicious node who plans to attack the system to steal coins. As a part of her plan, Alice could issue one transaction TA where she spent all her coins with Bob. But she could also issue another transaction TA prime where she spent all her coins with Carol. If both Bob and Carol observe their own transaction in some block, they will ship their supposedly paid good to Alice. Alice will then have double spend. She will have spent her given coins in more than one transaction. The problem is that TA and TA prime conflict. As the system is distributed, the Bob may not be aware of TA prime, that Alice is spending all her coins with Carol. This is because he is only able to see one branch of the blockchain. Likewise, Carol may not be aware of TA, that Alice is spending all her coins with Bob. So, how do we avoid forks? We need to have an agreement or consensus among the nodes that participate in the blockchain. We need consensus to totally order the block and maintain the chain so that it doesn't end up being a DAG. In other words, all the nodes must be in agreement on the block at each index of the chain. In the consensus problem, the nodes propose a value, and they must agree by deciding one value among these proposed values. So consensus can be defined as a problem along three properties: validity, agreement, and termination. Validity ensures that any value decided is a proposed value. By agreement, we understand that all the nodes will decide the same value. Termination implies that every correct node will decide eventually. If we want to solve the consensus problem, then we must solve all the problems associated with these properties. In distributed system where we have multiple nodes, the nodes communicate using message passing. This means to exchange information, nodes will have to send and receive messages. But in a distributed system, it is common to have failures of individual nodes. Essentially, a system fails when it cannot meet its promises. Let's look at two particular types of failures. The first one is crash failures. It says that the server halts but behaves correctly until it halts. The other type of failure is called arbitrary or Byzantine. It means that the server may produce arbitrary responses at arbitrary time. Let's take a look at an example of crash failures. Here the red arrow indicates the execution of the node P. The node P sends some message initially and then receives message before crashing. After it crashes, it doesn't interact. It doesn't send messages, it doesn't receive messages, it doesn't do anything. On the other hand, in Byzantine failures, the node P will send messages that may be outside the domain specification. It can also send messages as if it were flooding the network. It may also send or receive some messages normally. It would keep executing. It may decide not to send any messages while it is expected to do so, as if it were crashed. This node experiences an arbitrary failure. In order to find a solution to the consensus problem, we need to make some assumptions. There are some cases where it is impossible to find consensus. One famous impossibility result was published in 1985 by Fisher, Lynch, and Peterson. Their study showed that there is no solution to the consensus problem in an asynchronous system having n nodes and if the number of failure among these n nodes is greater than or equal to 1. This is regardless whether the failure is a crash failure or Byzantine failure. Another impossible result was published by Pease, Shostak, and Lamport in 1980. Their study showed that there is no solution to a consensus problem if the number of Byzantine nodes is greater than or equal to one-third of the entire nodes that are trying to solve consensus. Let us consider an example in which there are 5 correct nodes and 2 Byzantine nodes. Here, we are assuming that this system is synchronous. Here, as we can see, there are f is equal to 2 and n is equal to 7. Since f is strictly less than n by 3, in this case, we can find the solution to the consensus problem. However, the Byzantine nodes can forge fake identities to increase its number to compromise the system. If the number of Byzantine failures exceed one-third of the total number of nodes, this makes the consensus impossible. This is what we call Sybil attack. A solution to cope up with this attack is proof of work. The problem with Byzantine nodes is that they could flood the system with block proposal. So to prevent Byzantine nodes from spamming the system with blocks or any other messages, one can request a solution to a puzzle for each of these blocks or messages. As the puzzle is computationally hard to solve, the Byzantine nodes would require computational power proportional to the number of identities it wants to impersonate. The solution to the problem is called proof of work. The way that it works is by including a nonce in a block such that the hash of the entire block follows a specific pattern, like having a set number of zeros at the beginning. This mechanism, along with the longest chain selection, is what we call Nakamoto consensus, and it is used in popular blockchains such as Bitcoin. This consensus mechanism has its own drawbacks. In proof of work mechanism, all miners are competing with one another to mine the block. This results in an enormous wastage of computer resource, which is bad for the environment. Let's take a look at how consensus actually happens. Consider a scenario where none of the processes in our system fail. Suppose we have n equal to 4 processes that are all correct. Let's say that initially each of these processes have a different proposal presented as an integer, say 0, 1, 2, 3. They want to find the smallest value among these proposed values. In order to solve consensus problem, we need to satisfy the requirement for agreement, termination, and validity. To solve this problem, each node must send or broadcast its proposal to all the other nodes. Once each process receives all the proposal from all the other nodes, they decide the smallest value among these values. Let's look at the solution through the pseudocode. This pseudocode indicates the algorithm that each process PI runs. The process starts with a set of values denoted by capital V that initially contains its own proposal, say x. The algorithm executes by sending the values V that have not been sent yet to all the other processes. After receiving the values sent by all other processes, it stores all these values in the set of values, say V. It then decides the minimum value in this set of values. To get a better understanding of how this consensus algorithm executes, let's observe a particular execution using the 4 correct processes we mentioned earlier. Initially, each process only knows about its own proposal. After everyone sends its value to everyone else, every node learns about all proposals, 0, 1, 2, 3. Finally, as indicated on the right-hand side, all the processes decide that the minimum value proposed is 0. The decided value can only be one of the proposed values, indicating that the validity is ensured. The termination is satisfied because all the nodes eventually decide. Finally, the agreement is satisfied because they decide the same values. We can see that all three properties of the consensus problem are satisfied, and this algorithm solves the consensus problem. There are 3 types of complexities associated with any consensus problem: message complexity, communication complexity, and time complexity. Let us analyze these for above algorithm. Message complexity is the number of messages that are needed to be exchanged. Since each node sends its message to n-1 nodes, the number of messages transferred is n into n-1. Therefore, the message complexity is O of n squared. Communication complexity is the total number of bits that need to be exchanged. Here, let's consider B as the number of bits needed to encode an integer in a message. and the number of messages that are exchanged are n into n plus n into n minus 1. Therefore, the communication complexity is O of bn squared bits. The time complexity is the time it takes to execute this algorithm. It heavily depends on the time it takes to deliver a message, which is significantly larger than the time it takes to compute things locally. As all the messages can be broadcast in parallel, it takes only O of 1 message delays to exchange all these messages. Let's now see how we can find consensus in the presence of crash failures. In order to solve consensus when there are nodes that can crash, let's assume a synchronous communication in which maximum number of processes that can crash is f. Let's take a look at pseudocode to this problem. The algorithm consists of running a loop of f plus 1 rounds, considering the worst case scenario where each faulty system crashes one after the another. In each round, Pi sends to all other processes the value it knows that he has not sent yet. Pi then receives the values sent by others and stores these newly received values in V. After all these f plus 1 rounds, Pi decides the value as the minimum value among all the values of the set V. It solves the termination problem because the loop has a bounded number of rounds. It solves the agreement because at the end of the loop, all correct processes end up with the same set of value V. So the decided minimum value is same from all correct processes. Finally, it solves validity because the value that it has decided is one of the proposed values. Let us examine the consensus algorithm that tolerates crash failures in terms of complexities. As there are f plus 1 iterations in this algorithm, and in each iteration there are n into n minus 1 messages, the total message complexity is O f plus 1 n squared. As each message can transfer up to n values, each encoded with b bytes, and there are f plus 1 n into n minus 1 messages, therefore the communication complexity is O b f plus 1 n cubed. As there are f plus 1 iteration and all messages can be exchanged parallelly, the time complexity is O f plus 1. Message delay. Let's see how to reach consensus in presence of Byzantine failures. To solve for Byzantine consensus, we need synchronous communication, and the total number of processes must be strictly greater than 3 times the number of Byzantine processes. The Byzantine problem can be solved by using exponential information gathering algorithm. Here, each process maintains a tree structure to record the information it receives. The size of the tree depends upon n, the number of process or participants, and f, the number of failures. Each node of the tree has a level represented by a string of process IDs. The tree itself has f plus 2 levels with level 0 at the top going down to the level f plus 1 at the leaves. Each process at level k has n minus k children where k is between 0 and f. Initially, each process decorates its tree root with its proposal. The algorithm runs in f plus 1 rounds. In each of these rounds, process Pi exchanges the value it has received with all other processes, and they decorate the tree nodes with the value it has received. If the value is not well formed, it uses the curation null. Otherwise, it decorates the tree nodes level I1 to Ik with V such that Ik told I at the round k that Ik minus 1 told Ik that Ik minus 2 told Ik minus 1, and so on until I1 told I2 that its proposed value is V. When the tree is decorated, each process traverses from bottom to top to assign a new value called new val to each node. The value assigned to new val is the value which is most frequent among the new val of its children. If no such majority exists, null value is assigned. Finally, the process decides the new val of the lambda. Let us illustrate our big algorithm with a simple example. In our example, let's say we have n equal to 4 and f equal to 1. In other words, we have 4 processes in total, and one of these is Byzantine. In this case, process P3 is Byzantine, whereas process P1, P2, and P4 are correct. Now our EIG tree structure would have 3 levels as we have only one Byzantine node. Each of the 4 nodes at the level 1 has 3 children at level 2. Here, 1, comma 2 contains the value that the process Pi received from the process 2, who claims it has received this value from process 1 and that it is the process 1 proposal. Similarly, 1, comma 3 is the value 3 received from 1, which it has relayed back to the process Pi. Let's say that each of our processes proposed values 1, 1, 0, 0 respectively. To see how this algorithm runs, each process starts by decorating its root with its proposal. Here we ignore P3 tree as P3 is Byzantine and may act arbitrarily regardless of the information it stores anyways. In the first round, the process exchange their proposal and they decorate their tree with the proposal they receive from other processes. This value is the value that one has received from itself. This value is the value that the process P2 has sent to the tree P1. Uh, this is the Here we can see that the value proposed by P3 that it has told P1 is 0, and here the process 4 has told process P1 that the value it has proposed is 0. Here we can see that the process P3 has lied to P2 that its proposed value is 1. Here also process P3 has lied to P4 that its proposed value is 1. Uh, in the second and the last round, each node decorates its second level with what it hears from others about the proposal they have received in round 1. Here we can see that process P3 has lied to P1 that the value it has received from P1 is in fact 0, whereas it should be 1. Here also the P3 has lied that the value it has received from 2 is 0. Here the P3 has lied by telling P2 that the value it has received from 1 is 0. Here the process P3 has lied that the value it has received from P4 is 1, where it should be 0. After all the trees have been decorated, each process establishes the tree from bottom up to set the new values of the leaves. It also computes the new values of the internal nodes as the majority new val held by the children. Finally, it decides the new val of its roots that is guaranteed to be identical. Here, if we look closely, we can see that the number of children that a node at f level can have is n minus f. And out of these n minus f, f can be faulty. Therefore, in order to reach a consensus, n minus 2f must be greater than f. Thus, we need minimum of 3f plus 1 nodes in order to reach consensus. Let us now analyze how much does this algorithm cost. As we can see, the message complexity of this algorithm is quite straightforward. As there are f plus 1 round and f is typically less than n, and the number of messages is at most quadratic at each round, the total number of messages is therefore of the order f plus 1 n squared. As there are f plus 1 iteration, the time complexity is O f plus 1 message delay. The problem with this algorithm is the communication complexity. As the size of the message grows over time as each node informs all other nodes about what it has learned from all other nodes previously. It follows that the complexity grows exponentially in this case, with the number of rounds, leading to a communication complexity of order bn to the power f plus 1. In all the consensus with failure algorithms that we have discussed till now have assumed synchrony. Although synchrony is helpful to solve consensus, it is not realistic over the internet. It is naive to assume that the communication over the internet is synchronous, and there are too many factors that can delay the communication of the messages. These factors include natural disaster, unexpected congestion, human misconfiguration, and of course, malicious activities from attackers who want to delay communication in order to steal assets. Unfortunately, with pure asynchrony, we cannot solve consensus in the presence of failures. The key here is to assume partial synchrony, that is weaker than synchrony but is stronger than asynchrony. By assuming partial synchrony, every message takes less than a bounded amount of time to reach their destination. What is important is that the bound on the time it takes to deliver the message is not known by the algorithm. Partial synchrony is realistic because it acknowledges that the internet messages can be delayed due to hacking and other causes. This means that the communication over the internet will eventually be fixed, and if the message keeps being resent, they will eventually be delivered, which is sufficient. A very popular Byzantine consensus solution that assumes partial synchrony is PBFT, short for Practical Byzantine Fault Tolerance. This consensus solution relies on special processes taking a role of leader. The leader's responsibility for sending messages to all other processes. The process that plays the role of leader typically changes over time. In this solution, some client C sends the leader the value it wants to propose to the followers. The followers exchange messages and progress toward the consensus after receiving 2f plus 1 messages. This mechanism itself is not scalable. As the number of nodes in the network increase, the amount of data that has to be uploaded by the leader also increases. To conclude, the leader is the bottleneck that prevents the information to be exchanged rapidly between the nodes. It is therefore better for scalability that all processes propose transactions rather than having a leader trying to impose its set of transactions. The key to scalability is to decide the block that grows with the number of participants in consensus. Additionally, to leverage the bandwidth between all nodes, we must decide on a block that is contributed by multiple processes rather than just one. So instead of proposing blocks, let's have a process propose a set of transactions that will be included in the block. Let's see how this works. First, all the processes propose a set of transactions. Then they exchange this set of transactions between themselves. From there, the process decide a block. By doing this, they decide on a block that is not necessarily what any individual process has proposed. Likewise, the decided block can be the result of the union of several proposed sets of transactions. To maximize performance, we want to include as many transactions as possible in the decided block. In particular, we need to accept all valid transactions, even when they are proposed by a Byzantine process. The idea is to use cryptography to check that a transaction is signed correctly to decide whether it can be included in the decided block. The question that arises with this process is what happens if the transaction was forced by a Byzantine process? Well, if it was correctly signed, then the transaction would withdraw an amount, but only from the account of Byzantine process. The Byzantine process here won't be able to double spend if we ensure that the set of transactions are non-conflicting, and there are no subsets of transactions that withdraw a larger amount from an account than its balance. Assuming that these correct processes propose a proposal S, the set Byzantine consensus problem is for each of them to decide on a set such that the properties of the termination, agreement, and validities are satisfied. These problems are solved by DBFT, Democratic Byzantine Fault Tolerance, which uses two other algorithms, a binary consensus algorithm and a binary value broadcast algorithm, to solve this consensus problem. If you want to see how this mechanism actually works, I have attached some resources in the description of this video. The set Byzantine consensus is well suited for blockchain. However, each miner has to verify the transactions, which limit the scalability. As the number of miners grow, the number of transactions needed grow proportionally. Subsequently, this means that there is no way to leverage the additional resources to gain performance. This limits the blockchain scalability. However, if we look closely, it is not necessary to increase the number of verification with the number of nodes. When you are considering a model where at most t nodes out of n can fail, for example, if we take v strictly lower than n processes verify the same set of transactions, then another v processes can verify a different set of transactions in parallel, thereby improving the performance by saving time. Now, if v is equal to t plus 1 processes, all the response, if v equal to t plus 1 process all response that a transaction is valid, then one can be sure that this transaction is indeed valid. Because among these responses, there will be at least one correct process responding. If these responses are distinct, then one simply needs to ask additional t processes to know whether this transaction is valid. Among the total 2 t plus 1 responses, a majority will guarantee to become from correct processes. This technique is called verification sharding. With verification sharding, the more the system grows, the more the CPU resources we bring to the system, and the faster the system will verify all the transactions. From understanding what consensus mechanisms are and what are their importance, we discussed various types of consensus mechanisms, as well as their pros and cons. We looked at how we can reach consensus in the presence of failures. Finally, we learned about the democratic Byzantine fault tolerance and verification sharding, a mechanism whose performance increases as the number of nodes in the network increase. Thank you all for being with me till the end.